Assalamualaikum and hi everyone. This is an introduction course of Control System Design for Code ESE 542. This course emphasizes on the design and analysis of the control system in time and frequency domain techniques. The students will also be introduced to a software tool to implement technique in analyzing control system. This course is offered to EEE 241 Part 5 students. So for outcome-based education, this course has 3 learning course outcomes. The first one is at the end of the course, students should be able to apply basic theory of control system design. Second course outcome is students should be able to design controller using classical techniques. And the third one is students should be able to demonstrate understanding of controller design using software tool. There are 3 program outcomes related to this course. They are PO2, PO4 and PO5. So this is the CO-PO mapping for PO2, PO4 and PO5 with the 3 course outcomes CO1, CO2 and CO3. So CO1 is related to PO2, CO2 to PO4 and CO3 to PO5. So now we revise the basic control system, and I will introduce a few control system terms. So in this introduction topic, there are 3 learning outcomes. First one is to explain the difference between an open and closed loop system. The second one is to obtain transfer functions and identify poles and zeros. And the third one is to recognize second order system response. So all of these elements will be used in the next chapter of design the control system using root locus and also bot plot. Control system are an integral part of modern society. Numerous applications are all around us. A control system consists of subsystems and processes or plants assembled for the purpose of obtaining a desired output with a desired performance given a specified input. So this figure shows a control system in its simplest form, where the input represents a desired output. So this is an example of the automatically controlled system that we can create, whether it is simple system or it is a complex system. So control system is the study of how to make system do what you want. A control system is a mechanism that alters the behavior of a system towards a desired output based on the specified input. For example, consider an elevator system. So in this case, when the 4th floor button is pressed on the 1st floor, the elevator rises to the 4th floor with a speed and floor leveling accuracy designed for passenger comfort. The push of the 4th floor button is an input. Okay, this is an input that represents our desired output, shown as a step function in this figure. So this is your input command shown as a step function. The performance of the elevator can be seen from the elevator response curve in the figure. So this is the elevator response. This is the region where the transient response, and this is the steady state response. The difference between the input command and the elevator response is the steady state error. So this elevator system is designed based on the comfort of the passenger, patient safety and also convenience. An open loop system is where the input applied to the process under control which does not depend on the actual output. A general open loop system is shown in this figure. This is the input and this is the output, where the output is not connected through the feedback path to the input. So for open loop system, then do not correct for disturbance and are simply commanded by the input. So there's no error connection for the open loop system. For example, toasters are open loop system. Okay, toasters are open loop system, as anyone with burnt toast can attest. The control variable output of a toaster is the color of the toast. The device is designed with the assumption that the toast will be darker the longer it is subjected to heat in the toaster. Okay, this is the timer. So the longer the bread is subjected to heat in the toaster, the toast will be darker. The toaster does not measure the color of the toast. It does not correct for the fact that the toast is white, brown, or burnt. Nor does it correct for the fact that toast comes in different thickness. So this is another open loop system example, a loop dishwasher. A function as a toaster and also washing machine. It doesn't measure the dish cleanliness. So this is a closed loop system. The generic architecture of a closed loop system is shown in this figure. The closed loop system compensates for disturbance by measuring the output response, feeding that measurement back through a feedback path, and comparing the response to the input at the summing junction. If there is any difference between the two responses, the commanded variable of the input with the feedback path from the output, the system drives the plant via the actuating signal to make a correction. If there is no difference at the summing junction, the system does not drive the plant, since the plant's response is already the desired response. So that describes the closed loop system. So this is the definition for a controller, process, actuator, and also the sensor. So closed loop systems then have the obvious advantage of greater accuracy than open loop systems. They are less sensitive to noise, disturbance, and changes in the environment. Transient response and steady state error can be controlled more conveniently and with greater flexibility in closed loop system, often by a simple adjustment of gain, like amplification in the loop, and sometimes by redesigning the controller. We refer to the redesign as compensating the system and to the resulting hardware as a compensator. That's it for part 1. Thank you very much. We continue in the next part.